So welcome back everybody in the afternoon session. So we are turning together with the quantum era again. And let's see the next talk from my colleague, Péter Kovács from the Wigner Institute, who's working together with Zoltán Cimborás. And the talk is comparison of classical, digital, classical photonic and quantum photonic enhance for solving the PDEs as a case study. So please, Peter.
Okay, thank you very much. So yes, this work together with Zoltán Kolovsky and Zoltán Cimborás in this. Yes, I would like to talk about neural networks. I mean, how to solve partial differential equations with neural networks. And actually, before of that, I start with a personal joke, but it's not working somehow. Okay. So when I started to prepare to this talk, this movie came to my mind because actually this is my very first talk in this topic because I come from high energy physics. So that's why I came to mind this 40-year virgin, and actually I'm not 40 anymore. So it's so this very first talk, but I still hope that you can find something interesting in it. Okay. So this is the outline of my talk. So I start a little bit of an introduction of this physics for neural networks. And a specific case I give what is the Burger's equation which we try to solve. And actually we try to solve on a usual digital network, but also we try to do this on a classical photonic and a quantum photonic networks as well, and to try to give you what are the differences, what are the benefits of the other networks. So the first thing is that so it started some time ago that this physics for neural networks is nothing else that they use neural networks to solve ordinary and partial differential equations, which is, let's say this is a good thing to do. So actually they already applied to many, many equations, the heat equation, Poisson equation, Navier-Stokes equation. They used even for this kind of fractional equations or integral differential equations. They use many, many things. And another thing is that they use also the inverse problem, which means that you have a partial differential equation where you have some parameters. You don't know that parameters, but actually you have some data. And you try to fit that as well, some data. But the question will emerge, it's hard to see, yeah, because of the light, but it's okay. I try to say that why should we use this kind of neural networks instead of the normal numerical techniques like the finite element or finite difference finite volume method, which we already have. We have integrators. And I try to give you some answer to this. So the one thing is that there are partial differential equations which are very, very hard to solve, actually, numerically. One example is if you have a convection diffusion equation, and this is convection dominated, so there are very large gradients in it, then it's very hard to solve. So we have very very abrupt changes in the solution. Then the normal integrator can go wrong. That is one thing. The other thing is that the neural networks are universal approximators. You know that there is a theorem that if you have even one hidden layer and you increase the number of perceptrons to a very large number, then you can approximate any kind of function in LP, actually. So this is a theorem. So you can actually approximate any kind of function. The other thing is that if you use physics for neural networks, you don't need a mesh. So you can operate on any kind of scattered point in some omega. So I mean, this is some subset of Aradan. And the other thing, which is very good in case of physics for neural network, that they can incorporate observations and observation experimental data into the training. So you can use the equation as well and both search in a way. So in this talk, what I would like to do is that a specific example show that how this can be defined neural network in classical digital case, a classical photonic case, which is, I think, is a little bit less known, and the quantum photonic case. And I use this for this equation, the Burger's equation, to solve this and try to tell something about the differences and advantages of this. So this is a very general form of physics-informed neural network. So I have some nonlinear differential operator, which I put there some kind of UX. The UX is the solution, let's say, and I also can have some parameters, and I can have some fx, which is representing the data. So this is defined on some omega, which is a subset of arrow then. So this is very general. It has d in d dimensions, so that I have including the time as well. And beside that, I have some boundary or initial conditions. So this represents the boundary and initial conditions together, which defined on the boundary of this omega subset. So if I go to from this very general case, so you can apply to any kind of this kind of relation. So this is really general. But now I'm stick to a more simple case when it is only one plus one dimension, and this equation is like that. So there's only one time derivative, and this can be a nonlinear operator, nonlinear differential operator acting on X. So this kind of equation includes the several conservation laws, different diffusion processes, kinetic equation, etc. And the X is on some AB interval, and the time is also in some interval. In our case, it will be -1 to 1 and 0 to 1. So what we would like to solve is this so-called Burger's equation. So this is a nonlinear partial differential equations that can be found in fluid dynamics, nonlinear acoustics, gas dynamics, and in case of traffic flow. But you can see here is that is a different time steps the solution. So this is the exact solution. And it actually, what I can say here, that if you are not familiar with this equation, that this term is the nonlinear term. Here u acts like the speed of the wave. So if the value of u is larger, then the speed goes faster. So that's why this the top of this wave goes in faster than the rest of the thing. That's why it looks like that. Okay. So this we use different time steps for this different time step, the exact solution, and we use the initial condition as a simple minus sign pi function. So this was already known in. So they could calculate it in 1986. This the exact solution of that. Of course, it's not. You cannot write down simply. It's only in an integral form. But what we would like to do is to solve this with some neural network. So this is the layout of the neural network. So we insert the x and t coordinates into the network, connect it to some hidden layers. So we have, in this case, we have 6 hidden layers. And in every layer, we have some number of perceptrons, and we can change this, how many perceptrons we use. And for the input points, we have the boundary conditions. So the boundary condition is that at -1 and 1, it should be 0. Initial condition, which is a minus sinus function. And we choose equidistant point along the initial condition and boundary conditions. And within the in the XT area, we use 5,000 collocation points where which is sampled from a uniform distribution. Okay. And in the first part, we tried that we use sine activation function at the first 3 layers and some other function, the tangent hyperbolic, in the last 3 layers. And we also try to change MP from 2 to 50 to check how we can, what is the expressibility of our network. So in this case, the number parameter range from 39 to almost 13,000. Okay, and we use the TensorFlow and the Adam optimizer with a fixed learning rate, and we use the number of epochs was ranged from 5,000 to 10,000, and hopefully I show a video here how it goes if it starts. So this is how the learning goes. If it's so at the different time step, you can see that how it changes the solution. And downstairs is the training curve. So the both you have the total loss, the initial condition and the boundary condition loss separately. This is all just a solution for the different time steps on top of each other. So you can see that, of course, it trains quite well, and but it goes out because of this is because of the Adam optimizer that it goes out from time to time. But then, of course, it is not necessarily that you get the best solution when you wait until the next, but you can save the weights at some minimum point, and then you can say that this is the solution for this specific equation. So okay, so we don't have to wait for the then it goes like that, and then it reaches some kind of minimum value. Okay, and what we tried next is that changed MP even from 1 to 200, and in this way the total number of parameters changed from 15 to 200,000, and these are the minimum value of the total loss. So we keep track on that, and they depicted on a log-log scale. But here we can see here is that if we use this one of them, which is so the disk curve is with the sine plus the tangent hyperbolic activation functions, and as you increase the number of parameters, here you can see some kind of plateau. So even if I increase further, then the solution doesn't get better, basically. But if we choose some other one, we choose also this GALU, which is practically written here. So it contains the R function. So this is it's a version of the ReLU activation function, but is smooth. You can derive, and then this gets better and better if we go down here. So it just shows that it very depends on what kind of activation function you use in case of this. But we have to further analyze that what is the minimum loss which we can reach with this training. Okay, so that's about the classical digital one. So we would like to do this also with some classical photonic neural network. And what is that? So it's I try to explain a little bit because maybe it's not as well known. But so there are photonic neural networks, which is, let's say, in last year there was a paper about that, which is called this fully integrated coherent optical neural network. So what happens here is that there is some laser light goes in, is distributed to some input channel, and in this case, in the laser light, if you have some data, you can have the x and t values as in the previous one. So in general, this is a complex number, and you decode this complex number into this optical field, which is here. And the optical field, it goes into, so from now on, this will be some nodes here, and goes into the first this green thing, which is nothing else as the Mach-Zehnder interferometer mesh. So what it do? This do an arbitrary unitary transformation on this initial light. Then I have some nonlinearity, which is in this case this nonlinear optical function unit. And how this works is that some part of the signal sent into some resonator ring, and they claim that that various function can be realized. It's similar like that. You cannot give you the exact form, but it shows in this paper that you can reach very different activation functions with that. And of course, there is more layers after each other, and then there is some kind of readout. In the readout, you read out some property of the optical field, and then of course there is some kind of training that is very different than the classical one, because in case of an optical device you don't have memory basically, so you cannot do backpropagation in usual sense. The training is a little bit different, but still you can use this to do some training is in a way that you send the value and the value is a little bit shifted. So in this case, you can approximate derivatives here as well. Okay. But up to now, as far as I know, they only use this for classification problems, so not solve partial differential equations. And this really exists. So this is fabricated. So this is a photonic integrated circuit which done at MIT. So this is some silicon board, and all the components which you saw here are on this board. So this part is where they distribute the light. This is the Mach-Zehnder interferometer mesh, and there are different parts. Of course, I'm not experts on a atom experiment. I don't know all the details of that, how it works, but you have that part. Why it works to, okay, so before that, I showed that, of course, we cannot do this because we don't have the device, but we can simulate on a normal computer. So what is the difference between to doing this than the usual one? The first thing is that since you have this kind of layer structure here, that I mean, you have this kind of things. They have the input and the output, of course, are the same because they are unitary transformation. So that's why you need some kind of embedding layer. So have to put, if you have only X and T, you have to somehow put into this N node. So this can be done in different ways. Let's say you can do something which is called a Fourier feature layer, or you can do a spatial multiplexing. So you put xt on every input, etc. What we did after, which is very similar that the physical photonic device, is that we realize a transformation of the form that we have a unitary, some diagonal matrix, and another unitary, and plus some nonlinearities. And why we did that? Because if we use this kind of structure, this unitary times diagonal times unitary, this is nothing else than the singular value decomposition of an arbitrary real matrix. But we do with different things. So we initialize already this matrix is not start from a real matrix and go back. And we realized this with this program package, the Picasso, which mainly wrote by Zoltán Kolarowski here in our group. And so this can handle these kind of operations very well. And after it goes through several layers, then of course we need some kind of this uxt function, which is the solution of the Burger equation. And this can be done, for instance, if I add the outputs and so some of them and take the real part. But this is one possibility. Of course, you can have others as well. So you can also train that. What are the advantages of these photonic neural networks? The first trivial thing that the light travels at light speed. So they are very, very fast, much faster than normal electronics. So it can operate at terahertz frequencies, so far beyond the normal gigahertz speeds. The other thing is why they started to do this is the ultra low power consumption. So there are passive photonic components like beam splitters and phase shifters. So they consume little or no energy. So they claim that in this compared to the digital circuits, it can have a factor of 100,000 less than the power consumption than in normal digital circuits. The other thing is that there's a very low latency, so it instantly goes through the light, so you don't have to wait anything, and there is no clocking and this kind of stuff. And another advantage is that you can pack multiple waves on top of each other. So it's so different. You can put different data on different wavelengths, and it goes through simultaneously on this network. And the last thing is that they don't generate too much heat. So it's much better because in case of normal computer, there is an issue that you have to somehow cool down the processor in order to work. In this case, you don't have this. Okay, so now I switch to the quantum version. What we can do in case of the quantum neural networks, one can use a continuous variable quantum neural network, which means basically the following, that you have some kind of quantum gates, and with this you can define something which is very analog of the classical photonic neural network, or even a classical network. And this consists of several things. So the information is coded in continuous value of position or momentum. So so this is the eigenvalues of the position and momentum operator. And there is two representation, the wave function and phase space representation, which you can think of that. And there are different kind of gates which operates or either on only one node, like the rotation, displacement, squeezing. So these are single mode Gaussian operators, and there is a two mode operator, the beam splitter. So this is very similar in the classical photonic case. And actually you don't need more gates than this. Besides that, there are also non-Gaussian gates, the cubic phase gate and the Kerr, which is usually used. So in this U, there is only the beam splitter and these rotations. And so a general CVQNL layer looks like this. So there is some unitary transformation, some squeezing, another unitary transformation, some displacement, and finally there is some Kerr operation. And with this, you can reach very similar neural networks as in the classical case. How this was used is, first, sorry. So why we would verse to use this kind of networks compared to the other one is basically, actually in Sophia's talk is already talked lots of benefits about that one. So the other thing, the one thing is that very high dimensional feature space. So the Hilbert space is quite huge. So that's why it can code, even with a small number of modes, you can encode extremely rich features. And the other thing is there is intrinsic nonlinearity via the measurement. So the measurements serve as a built-in activation functions. You don't need add anything special. With the measurement, you can realize nonlinearity. And the next thing is that there is quantum entanglement. So the input modes can capture correlation, which is very hard to capture with the classical networks. And of course, since we have superposition, you can use many input states simultaneously. That's another thing. And of course, this enhanced expressivity, because with the very small circuits, you can match with a much higher classical component. And what was done in a very recent paper is that they used this kind of quantum photonic layout to solve not the Berger equation, but the heat equation. So it's a little bit simpler equation. How they did this, that they encoded the x and t values with the displacement operator, and they sent it a very, very small network. I mean, there's only beam splitter, some rotation, squeezing, beam splitter, rotation, two displacement and Kerr operators, and then some measurement. And with the measurement, what they did is that at the one output, this txt is the same as the uxt earlier. So that is the solution of the now not the Berger but the heat equation. And on the other output, they expect to have the derivative of the solution. So in this case, this is a little bit different, because earlier they didn't use this technique that in one measurement they get the solution, and the other the derivative of the solution. 1 minute. Perfect. Okay. So some differences that I only tell you about the loss terms, because which I didn't emphasize earlier, that of course you can have different terms. So for the equation itself, the initial condition, boundary condition, and in case of quantum photonic layer, you have something which is called the consistency term, that this should be the derivative of this output, and the trace term, which ensure that the state is, so the trace of the state vector is 1. Okay, but you can have here some kind of weights, and depending on the training, it maybe is beneficial to increase some of the weights to differently as the other. So in this case, they say that the initial condition should be much larger than the other one. The training will be put in this way. So I reached actually my end of the talk. So I would like to demonstrate that we can use for the same PDE, we can use the classical digital, classical photonic, and quantum photonic neural networks. So this is already, so this is a work in progress. So we haven't finished yet the all these in all these networks the calculations, and but I think it's worth to compare them for a specific text that either to find out that which one is better, and which you can also not see. But this I refer to the talk of Zoltán Kollárowski because maybe in our case we can use this, was already mentioned by Péter Rakita, this approximation that we calculate along the line the derivatives, and maybe it can help the training better. Okay. Thank you very much.
Okay. Thank you very much, Peter. Congratulations to lost your virginity in quantum. Questions for the audience?
Well, in the case of pure photonic realization of what you presented, was this the mesh making the unitary transformation, and there was a nonlinear term.
Yeah. Yes.
I couldn't catch it. Can you program them? How they look like?
Yeah, exactly. So you can program it. So in the mesh, there are some. So there are beam splitters, and actually you can change the angle inside the beam splitter. I don't know the exact ROM because it's quite so I don't understand the engineering part, but I can search for you. I can tell you that which maybe they can do with temperature, changing the temperature or something like that. So it's very easy. So they don't need. I mean, they don't need some extra electronic, because if you put their electronics, then it will be much slower, and then of course this is not the way.
You can change them individually.
Yeah. Yes.
Quick one. So just because I might have missed it. In the physics informed neural network, the physics information is in the loss, correct?
Yeah, exactly.
So,
exactly.
but not in the topology. You don't use this.
No, actually, what you use that you write down the PD is you reorganize to get 0, and basically this put this the square of that you put in the loss, and that's it.
Thank you so much for the talk. I'm curious, you mentioned that you don't have derivatives for the CVQNN layer. Did you use any optimization methods that don't require derivatives, like SPSA or other types of methods that could
Actually, we plan, but we are not yet there. Okay. But we plan to do several things. Okay.
Sure. Yeah. Thank you.
Thank you.
Any further?
Yeah. Exactly. Yeah, that is a very, very good question. So the thing is that if you usually what they did up to now, that they set some specific initial conditions, specific boundary conditions, try that one. If you, let's say, you have then the weights, fix the weights, and try to, let's say that what is the solution for another initial condition, it won't work usually, because then you have to apply some different approach. Now you can define this kind of networks as well, where you fit to multiple initial conditions in some sense, but this is a very new direction. So that would be the aim of this. Do you have a more general solution? Yeah. But that's, thank you.
We have to stop here and move on. Let's thank Peter again.